Hello, everybody. So what we're going to be looking at today is going to be something that we call solids of revolution. And specifically, we're going to be calculating volumes of that kind of thing. Um, Now, this is a new topic for us. You're not supposed to know anything about it going in. We're going to end up using an integral to do this, which, makes sense based on where we are in the book. Um, yeah, and so let's go ahead and get started. So before we get into the actual topic of solids of revolution, I just want to mention a couple things that you already know about area and volume. And there's a connection between area and volume that you probably have never had to really think about very hard. Maybe you noticed it. Maybe somebody told you, one of your instructors. Maybe they didn't. So it's not a big deal. We're going to talk about it right now. So let's say you have a shape like this, all right, just a rectangle. Uh, and so the width is just X and the height there is Y. And of course, you would be able to calculate the area of this rectangle. That'd be very easy, right? So I'm going to use A for area. Um, it would just be X times Y, right? And that's a very simple idea. And if we're going to look at the volume of a shape now, so let me draw a shape. I can do this. Hold on. I was harder than it thinks. Harder than it looks. It's not actually hard. It's just I was trying to think about which way I wanted it oriented here. Most. I didn't draw that straight. Oh well. Okay. That's terrible. I'm gonna redraw those last couple of lines. Sorry about that. Just draw it. Oh, killing me. Okay. So let's look at a volume now. And I want to again have like a length and a width and a height and everything. And it doesn't matter what is what. So here's what I'm going to do. I'm going to call this X and I'm going to call this Y. And the reason I'm doing that is so that this shape right here looks kind of like this shape right here. Uh, don't worry about like why is X here and Y here. It doesn't matter. They're just three different variables. Okay, and then let's put Z there. And, I bet that you know how to calculate the volume of this. You probably at some point learned that the volume of a rectangular box was X times Y times Z, right? Of course you know that. But another way to think about that is that the volume of this box is actually related to the area of the side of the box. So how is it related? Well, let me draw the picture again. I mean, of course, you know how it's already related, but take that, duplicate it, move it down here, like so. And so if you think of taking just the side of this box here, right? That right there has an area. That area is what? Area is X times Y, right? And so if you think about it, then you could rewrite the volume this way. So the volume is also V equals not X times Y times Z. It is X times Y times Z, but you can think of it as just the area times the Z. Right? So if you calculate this area here, then you just multiply it by this third dimension because the area already has two and two of the dimensions. And you can extend that to different kinds of shapes. So like if I have a cylinder here or a circle first, also, hold on, what am I drawing? Circle. So if you have a circle like this, and circles are usually will have some kind of radius, right? Didn't happen in this case. It will not do it. Draw another circle where I go on the lines. That's also not going to work. There we go. That should work. It still doesn't do it. Come on, draw a straight line. Okay. R. So there's a circle, right? And if I wanted to know what the area of the circle is, you know that. It is pi r squared, right? Now, what about for a volume? What if you were looking at a cylinder? I will draw it right side up this time. What's it doing this? Sometimes it'll want to draw straight lines and sometimes it won't. Yeah, okay, fine. That's terrible, but good enough. Okay, I don't care. I don't care. So there's a cylinder. And at some point in your life, you probably also learned how to find the volume of a cylinder. And if you did, you probably learned that it is pi r squared h. Well, where's the h, right? The h is going to be the height of the cylinder. But again, you can think of that as being an area times the height, because if you just take this area here, right? And if you call that area A, then you could rewrite this volume that we've got as simply the pi r squared, right? The pi r squared part is just the area. So it's the area times h, right? And so the same concept applies here to this cylinder as applied to this. Actually, in a lot of math classes, you would also call this a cylinder. Cylinder doesn't necessarily mean the top is round in math. It does in real life, right? Like if you called this a cylinder, people would think that you were just, dumb. But in math, we call that a cylinder. Cylinder is anything with a shape, and then that shape is extended along an axis like this, like extruded along an axis. So there you go. Now, what was the point of this? The point of this was this concept of an area times a height, or an area times a length here, giving you a volume. That's really the whole idea that we're going to be dealing with for the solids of revolution, which is today's concept. Okay, so let's just mention that last bit again. So the concept is, if you've got any kind of shape, it doesn't matter what kind of shape. So like I can draw a shape like this. And if I just say that it has some kind of area on top, whatever the area is, and then you extend this shape along an axis like this, and you wanted to know what the volume is, the volume is an area times, that's like a times, maybe I shouldn't do that, I'll use a asterisk or something, no, just a dot, some kind of length. So an area times some type of length is a volume. And so like in this shape right here, like if I called this A, and then I called this H, then of course, what would the volume be? It would be exactly what we've been talking about, A times H, right? And you can calculate the volume of any kind of object like this using a formula like this. And that's a pretty basic concept. It's not that hard to understand because you've already seen it before in your life for calculating the volume of a shape like this or a shape like this. So what does that have to do with us? So what it has to do with us is we're going to be talking about what we call a solid of revolution. Solid of revolution. So the basic idea for a solid of revolution is this. So we're going to be looking at, I shouldn't do it that way, I should put it up here. Extend that down here. You've got some kind of shape. This is just the normal X and Y axes. We're looking at a graph now. You've got some kind of shape here, whatever it is. Not that. Like that. So you have a curve, but we're going to take this curve and we're going to extend this down to an axis. Like this. And then that right here forms an, which is not the area that we were talking about up above. So don't think it does. Oh, that's weird. I can't really color that in very well, can I? Okay, good enough. So you take a shape like this, and then what we're going to do is think about making this into a three-dimensional shape. And so we've got an axis here. So this will be our axis of revolution. And again, in 3 dimensions, we're thinking about taking this entire curve and spinning it around the axis, right? So every point on here gets spun around the axis. I should draw those like more like this. Redraw this one. All the way around. And if you take a shape like that and you spin it all along the axis, then what you end up with is a 3-dimensional shape that looks something like this. Let's see if I can draw it. Right, so this is your, I should draw that in red like I did on the other picture. And then you've got your curve. Let me draw the curve in blue over here. Curve that's up here. But the curve has been rotated around and in 3 dimensions. And so you end up with this kind of shape. Does that make sense? I think it makes some kind of sense, right? Yeah. So that's the idea of a solid of revolution. Let me draw a couple more just to see if we really get it. In case my first shape here was not good or something. So what other kind of shape can we have? Yeah, let's just do like this. That'll be fine. An endpoint there and an endpoint there. So if you take a line like this, and again, we're rotating it around the same kind of line here. Sure, that'll work. If you take every point on here and you have to rotate it around the axis, right? Like, so the point up here, you go all the way, you trace a curve all the way around the axis in 3 dimensions. You get something like that. If you go in the middle, you get something like that. If you come down here, you get something like that, and so on. And then when you're done, what does the shape look like? Hopefully you can see that it makes sense that this would be like a cone, because you're going to get something like that for your shape, right? So this is actually a circle here. We're just looking at it on, you know, at an angle. So these are solids of revolution. Revolve, right? That's what's happening from the picture on the left to the picture on the right. So we're just taking a curve and we're rotating it around some kind of axis, and then we're getting a shape. And sometimes there's even holes in the middle. Let me draw one of those, see what that looks like. What will that look like? It'll be a little bit hard to draw, but let's say I do this. Let's say I go um, this, nope, this, and then like that, and then I go like that, and then I color this in, and let's say you rotate that around the axis. Again, this is still the axis here of rotation. So in this case, because it's not just a curve, you've got like actual like shape there. Um, maybe it'll look a little different, right? So like every point in this region gets rotated around the axis. And so when you do that, you kind of think of it as having like, no, not that. Hold on. You kind of want to think of it as, well, there's a curve down here, right? And that's going to get rotated around like that. And then you've got this outside curve here, and that's going to get rotated around, which is going to be obviously make a bigger shape. And that's a terrible, terrible picture here. And so terrible that I'm going to delete a lot of that. And say, if we just rotate this entire thing around, what are we going to get? Well, what we're going to get is basically a bowl, right? Because what's going to happen is you're going to end up with a ring like this. Right? And here in the middle, it's going to be kind of, hollow center there. It's a bowl, basically. Does that make sense? Um, because if you rotate like this around, right, there's nothing here. So in the middle, if you rotate this around the axis, there's nothing there still. But if you rotate this part where there is something around the axis, then you get the edge of the bowl. So I mean, I think that hopefully makes some kind of sense here as far as what kind of shapes we're going to be getting. Um, and now that you have hopefully some kind of sense for this, what we're going to do is we're going to talk about how do you calculate these things? Like how do you calculate the volumes? Okay. And so how will we do it? So what we're going to be doing is we're going to be doing it with an integral. This is the idea of the integral. It's not a proof, but this is the idea of how we're going to calculate these things. So what's our setup going to be? So for the problem, so this is the actual calculus stuff here. So calculating the volume of a solid of revolution. Okay, so I guess we're going to need to define exactly what we're talking about. But first, what we're going to talk about is just kind of why we're doing it the way we're doing it. So let's write the idea first. So I'm going to draw just a shape here. Okay. So well, okay, you know what? Maybe we'll just actually derive it. Oh, I need to put that in the middle. Okay, sorry. So let's say you've got this curve here. I want to just, it doesn't need to be a particular curve. So I'm just going to draw it like this. And so let's say this is A and let's say this is B. Okay. Now, and then let's say that this curve is y equals f of x. Okay. So there's your curve. All right. Now, if you took this and you were going to rotate it around the axis, we know what that would look like now, kind of, right? That's pretty much the first picture that we drew. Um, what we would have is a shape like this. Um, shape like that, right? I guess I probably shouldn't have drawn that. I'm trying to draw it. You wouldn't be able to see through it. Um, so something like this. And it doesn't need to be perfect. Okay. You end up with something like this when you revolve it. Revolve around, in this case, the x-axis was the axis, right? Right here. Axis. Okay. So we did that. But how are you going to calculate the volume? Well, we don't know how to calculate the volume yet, but you could estimate the volume like this. You could estimate the volume as follows. Okay, so you could take your original shape, which I shall duplicate. No, that would not duplicate. That is duplicate. So you could take your original shape like this, and instead of using this function, what if you thought of it just as being kind of stair steps, right? That's not the same shape, right? But isn't it kind of close? So each of these is just a horizontal line like that. You could estimate the function. As horizontal line segments. Okay, and let's suppose each of these line segments actually had a width that I knew, and I'm going to call that width delta x. So each of these has a width of delta x. So like this is delta x, this is delta x, this is delta x. I know they don't all look delta x in my picture, but let's suppose they're all delta x. Okay, then what you would have for your volume would be a different looking volume. What your volume would look like would be a little bit tricky to draw, but something like this. Right? So it wouldn't be this type of thing with a nice smooth edge to the volume. It would be something like this where it's stepped. Because the function is stepped, then the volume is stepped. But the reason we care about that is because each of these shapes is now a separate cylinder. That's a cylinder, 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 right? It looks like a wedding cake turned on its side. So on the picture here, what you've got is every one of these has a delta x width or height, like that. And then each of them has on their edge a circle, right? We're looking at this at an angle, so this is a circle, right? And we know how to calculate the volume of a circle, no, the area of a circle, but you would need to know the radius, right? So like this would be like a certain radius here, like R1. I guess I shouldn't call that one R1. I'll call that one like Rn, right? The first one, oops, like the first one has a radius of R1, and then like the second one has a radius of R2, and the third one could have a radius of R3, right? Dot, dot, dot. Um, this one is Rn minus 1, and then finally Rn. Does that make sense? And so what you end up with is a bunch of cylinders, right? A bunch of cylinders. They're short, fat cylinders, but cylinders nonetheless. And so each one has volume like V, I'll say like I, because like the V1, V2, V3, so they're all V something. VI would be, it would be pi Ri squared. That's the area on the side, right? And then to get the volume, you'd have to multiply by this delta X, right? Something like that. You have an area and then you have a height, right? And so knowing that you have this area here and then you just multiply by this delta X height to get this volume, that was the idea that we were talking about way up here, where we're saying if you have an area and a height, you just multiply the area times the height, right? Area times the height to get the volume. So that's what we're doing here. Each of these is an area on the side, and then the height is actually sideways. So something like this. So like I could have written it this way, right? Like area times delta X, and the area is on the side. But we know that the area is a circle, so it's like pi r squared delta X, like that. I think, did I put the pi in parentheses before? If so, that's wrong. Something like that. And you could even go further, because you can say that, how are you going to get the radius? Like the radius over here is different than the radius over here, which is different than the radius over here. And the radius is actually going to come from this function here, right? Somehow. The radius is like this distance, or this distance, or this distance. So big radius here, small radius here. Small radius, big radius. So the radius is actually a function of x. And so you could say that each of the r's is actually a function of whatever, it's like some x value there. And then times the height. So each of the volumes is something like this. So if you wanted to add up the volumes, what would you do? So if you add, so if you sum up all of the volumes, you know, I'm not really being rigorous about how many there are or anything. It would be a summation, right? Remember this? Summation, and we would just add up all of these. Pi, all of the radiuses, radii, and then times delta x. So like this right here is your area, and then that's your height, basically, for the cylinder. So this is just the area of a cylinder. And you would have to do that for however many slices you made. Okay? So this is right here. It says area of a circle. Right? And then this is like a separate, oops, I hate it when that happens. This is like a height. And then if you take all of this together, what is this? That's the volume of one slice. Which I was calling each of these a slice. So slice one, well, slice, 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 sliced up into cylinders. Okay, and that's the idea. Now, the part that I'm going to hand wave here is you would say, well, that's not going to be exactly the same area as what we wanted, right? Like this volume is not the same as this volume, because this one's got flat edges and this one has a round edge. So they're not the same. Now, what would you do to improve your approximation here? The way you would improve your approximation is you would use smaller and smaller line segments, right? Instead of little, you would make delta x smaller and smaller, 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 smaller. So if you use 1, 2, 3, 4, 5, 6 slices, you get an approximation. But if you used 10 slices, your picture would be better. And if you used 100 slices, your picture would be even better. And if you used 1,000 slices, well, if you used 1,000 slices, you might not even be able to tell the difference between this picture and this picture if this one had 1,000. Okay, so the number of slices goes up, the approximation gets better. So as the number of, we'll say, slices goes up, the approximation is better. Volume is better. And if it goes to infinity, right, n is the number of slices. So if n goes to infinity, it will be perfect. So not even an approximation anymore. All right, so if n goes to infinity. Now, what happens when n goes to infinity to the number of slices? Well, it turns out, let me just write this, volume. Approximately, let's just say approximately that. So what happens to a sum like this as n goes to infinity is it becomes an integral. And we should have talked about this in an earlier lecture when we were talking about Riemann sums. But basically, the hand-wavy thing is this. So the sum is going to become an integral. And this right here is going to stay pi r squared. But there's not going to be any xi's anymore. And then the delta x becomes the dx of your integral. Okay. And then this is an integral symbol. It's going to be a definite integral. So what should the limits be? Well, the limit here going up to your picture, that's going to be the starting and stopping values here, the a and the b. Like that. And this right here is what we call the disk method for calculating the volume of a surface of revolution, solid of revolution. So I'm going to box this, and I'm going to write that this is going to be the formula for the disk method. And this is only going to be the disk method when the when the axis is the x-axis. It gets more complicated in other situations. What did I call it? Axis equals x-axis. Okay, so that's the thing. So what are we going to do with that? Well, what we're going to be able to do with that is we're actually going to be able to calculate some volumes now. So let's try it. So here's an example. Let's let, doesn't really matter what we use here. So let's let y equal, let's say 3, I don't want 3x, 1/3 x, 1/2 x, 1/4 x, plus 1, be a curve. Okay, rotate the region under the curve. So I have a curve above. So we want under the curve, above the x-axis, and between, let's say x equals, let's say 1 and x equals 8. So that's a region under the curve above the x-axis between x equals 1 and x equals 8, around the x-axis to obtain a solid of revolution. What is the volume of the solid? All right. So what is the volume of the solid? So first of all, we want to make sure we know what we're talking about here. So let's actually look at this function. So you can use a computer to help you with these if you want. It's not strictly necessary. So like I can do this. I can look at this curve. Oops, no, I can't. I can look at this curve here, and this is just a straight line, right? This is not super complicated. 1/4 x plus 1, it's a line. The y-intercept is 1. The slope is 1/4. So I can graph this by hand. So the y-intercept is 1, so it goes through there. And the slope is 1/4, which means up 1 over 4. So I can just go like up 1, 1, 2, 3, 4, goes through right here. Up 1, 1, 2, 3, 4, goes through right here. 1, 2, 3, 4, goes through right here, right? That's not like a super hard, not a super hard function to graph. A straight line. There you go. So there's your y equals 1/4 x plus 1. Okay, now that's not the region, right? That's just the curve. But they describe the region as supposed to be under the curve. So under the curve is everything here, right? That's under the curve. But they say under the curve above the x-axis. Okay, so it's not what I shaded. Now it's this. Oops. Now it's just this. That's under the curve above the x-axis. But then they say between x equals 1 and x equals 8. Well, that's not what I graphed here, so erase it again and say, well, where is x equals 1 and x equals 8? Well, we didn't put those on here, but we can do it, right? This is 1, and then we got 2, 3, 4, 5, 6, 7, 8, right? Fill those in. So the actual region we're talking about now is just between x equals 1 and x equals 8. So this is the left-hand side and this is the right-hand side, and we only want the area between here. So we're only talking about this area now. So you have to understand what the area is that they're talking about, the region they're talking about. And so this is the region because it's under the curve, right? Curve on top, under the curve, above the x-axis, between x equals 1 and x equals 8. You have to understand that shape, okay? Then what we're going to do is we're taking this, and they say we're rotating it around the x-axis, right? Rotate around the x-axis. Rotate around the x-axis to obtain a solid of revolution. And we know what that's going to look like because we've looked at a couple examples. So it's going to go around there. That's going to go around there. And when we do that, you know, what's the shape going to look like? You know, something like that. Right? And there you go. That's basically what the shape's going to look like. Rotate. Okay, but we want to actually solve this with an integral. And so looking at the formula here, this is all fine, right? We got the axis is the x-axis, pi is pi, dx is dx, a and b we can figure out. What's the r? And so the radius, the r, you always measure the r from the axis up to the curve. So you measure R from the axis up to the curve, which on these simple problems, it almost seems like you don't even need to bother, but I like to. So measure R as from the axis, which is not always the x-axis. That's why I'm saying the axis of rotation up to the curve. Okay, that's your first step. So it's just like, this is the x-axis is the axis of rotation, right? So you're just measuring from down here to up here. That's your R. Okay. So it's very simple. Now, because it is very simple, it almost seems too simple, but the idea here is, how would you measure that height? And the height is different over here than over here. I drew it in the middle, but you could have measured it anywhere. What is this measurement? Well, it's just this distance, but this distance is actually just given by the y value of the function, right? Like if this is 1, 2, 3, right? Right here at this point, what's the R? Well, it's 1, 2, 3. Right? Over here, it's just 1. No, it's like 1 and a little bit. Here it's 2. Right? So it's 3, it's 2, it's almost 1. But it's just the radius is just given by actually just this function here, right? Like if you put in 8, you're going to calculate a 3, which is the y value, and the y value is actually the radius. So it's just the y value. So in this example, it's just the y value. So what is it? It's 1/4 x plus 1. Okay, so hopefully that's not super hard. That's the radius. Just calculate it from the y value, and then you set up your integral. And so your integral is going to tell you that the volume is the integral from a to b of pi r of x parentheses squared dx, like so. Fill in your radius. And in this case, this is what we call the disk method. We've only looked at disks, so that's why it's the disk method. I'll mention why momentarily. So let's see if we can fill this out. So what should we have for A and B? Hopefully you can see that they should be 1 and 8, right? We're going from 1 up to 8. Right? 1 to 8. We have the pi, parentheses squared. You put your radius in here, but it's squared. This is the radius. It's just the function. In this case, it's just the function. And then you've got your dx on the end. That's your integral. It's easy as that. So it wasn't that hard, right? Like all we really did was fill in this, all we really did was fill in the R here and the A and the B. Once you fill that out, you should be able to integrate to find volume. So how would we do that? Well, the first thing you can do is you can actually just take this pi and using the rules for integrals, move the pi out of the integral. You don't need it inside. In here, this, you're probably going to have to FOIL. Not probably, you are going to have to FOIL that, multiply it out. So you multiply this out, it'll become 1/16 x squared. And then you're going to have 1/4 x times 1, which is 1/4 x, plus 1/4 x is not an eighth, half. And then 1 times 1 is 1. So I just multiplied that out. Right, so that's just FOIL. Hopefully that's not a problem. And once you do that, how are you going to do it? Power rule, right? So we need power rule here. So we're integrating this with power rule. So that's 1/16. And then how do you integrate x squared? It's going to be x cubed over 3 plus here the x squared over 2, which I'm going to write x squared over 4. Just combine it with the half that's already there. And then 1, you integrate 1 and you get x. Okay, I'm going to rewrite this one more time. So x cubed over 48 plus x squared over 4 plus x. Should have put that in square brackets. Can't do it now. 1 to 8. And then you fill in your 1 and you fill in your 8. So you go parentheses 8 cubed over 48 plus 8 squared over 4 plus 8 parentheses minus, that gets a pi 2. 1 cubed over 48 plus 1 squared over 4 plus 1. And you work this all out by hand if necessary. 8 cubed is 512 over 48. It's not going to go in even. It's 10 2/3, which is that 32/3. Yeah. All right, so I'm kind of cheating. I have a calculator that doesn't do fractions right now. That's 32/3. This is 64 over 4, which is 16, right? Plus 8 minus, and in here you got just 1 over 48 plus 1/4 plus 1. Fractions. So I'm just going to type this into like Wolfram Alpha or something just to do the fractions real quick. I should have used a calculator, a scientific calculator that does fractions. That would have been nice here. 32 over 3 plus 16 plus 8 is 104 over 3 minus pi 1 over 48. Oops. Plus 1/4 plus 1. 61 over 48, is that? Wait, yeah, that's right. Okay. We got to subtract these, so it's actually pi 104 over 3 minus 61 over 48. If you factor out the pi, 104 over 3 minus 61 over 48. And I get 1603 over 48 pi. Now that's a weird number. If you get a decimal, it's approximately 33.39. Uh, 40 actually, if you round. Okay. And it's a volume, so it's units cubed, whatever the units are. Now, does that make sense that it's like 33? Well, if you come up here, right, just think about this, right? Like this distance is 3, and then this distance is like a little bit bigger than 1. I'm gonna say like 1.2, making it up. You know, so does it make sense that this total volume is like 33 based on these kind of numbers? And then like we know that this distance is like from here to here is 7. Sure, right? Like if you multiplied these all together, 3 times 7 is 21. Actually, the height would be 6. So like 6 times 7 would be like 42 times 1.2 would be like around 50. But this is a bigger radius, so it's got to be less than around 50, right? So just let me just say what I just did again, right? The height here, well, what's the area of the side? Pi r squared. 3 times 3 times 3, right? Or pi r squared. So the radius is 3. 3 times 3 is 9. Times 3 is 27. So it'd be like 27. 27 times 7. Would be 189. Okay. But this is very small on this side, so it's got to be a lot smaller than 189. Whereas this side here has a radius of 1.2 ish. 1.2 squared times pi. About 4.5 times 7 is 31. I feel like I made a mistake here somewhere actually, but there's probably a small typo somewhere. But anyway, the point is that this is a volume and it's supposed to be the volume of this shape here. Okay. We set up the integral correctly here. This is correct. But it's always possible that I made a mistake when I worked this out. So anyway, what's the point? The point is that this basic method of this formula for the disk method, filling in your radius, and then your endpoints, and then solving the integral, that's really what you're going to be doing on 90% of the homework. Well, I shouldn't say 90%. We'll say 75% of the homework, and then 25% is slightly more complicated. But you're just using this formula over and over. And we're going to have a second lecture on this where I cover more examples and the more complicated ones. Okay, so I'll talk to you guys later, and good luck with the homework.